This semester we're going to be working quite a bit with systems that continuously change. There's no real steady state. The velocity, the acceleration, they're all changing. In Physics 215, when you talked about acceleration, typically you left the acceleration as a constant. Well, this semester we're going to be looking at systems where the acceleration is changing just as much as the velocity and the distance. So the only way that we can actually deal with these kind of systems is working with differential equations. Now, we've been we're looking at acceleration as a constant in other systems, and so we always think about having some differential of velocity as being some constant. So we had, in looking at forces, we had a very general formula: mass times acceleration. And we noticed that we could take and move this into a differential by saying, well, mass times the derivative of velocity. Or we could take it down further and say it's the mass times the second derivative of distance. So this idea that things are always changing, and now if I put this into a more general term, what we're going to be doing this semester, let's say we have a force, it's a function of t, then that means that, well, the mass we usually keep constant, so the acceleration is a function of t, which means then that the velocity is a function of t, and the distance. Now we've said that before in the equations above, because we have some derivative with respect to t, but we're putting this explicitly in this form because what we're showing here is that the acceleration is no longer constant. Now, this is going to be important when we talk about oscillations, and we'll even see how the formulas will relate when we talk about electrical systems. So in chapter 14, we talk about springs and pendulums. But by the time we get into chapter 30, we'll talk about electrical oscillations. And the equations that describe springs and pendulums are also going to be the same forms that describe electrical oscillations. We're also going to be getting into some first order differentials, and that's going to be when we talk about a capacitor that's charging. So just as an overview, let's say you have some resistor and a capacitor, and that's hooked to a battery. Now, I know this is probably a little bit strange to you at the moment, but just so that you kind of understand, these are electrical parts. And we'll have some kind of electric current flowing through this circuit. And the rate that the charge accumulates on the capacitor is going to be dependent upon the potential difference between the capacitor and the battery. So you're going to have some dq for charge, dt, that we're going to need to solve. So there's a lot of differential equations that we're going to be dealing with this semester. And really, there's no way to understand it unless we get into a deep discussion of differential equations. But here's the point I want to make. These differential equations are very specific. This is not a complete course in DiffEQ. We're only going to look at the ones we need. We're not going to get into the more extreme forms of differential equations, only the ones that we need. And really, to solve these, you need Calc 1, believe it or not, and Trig with a little bit of complex numbers. You can do it without, but complex numbers really help you out, make things a little bit simple. So this is where we're starting out, and so the next 18 lectures and little snippets for the differential equations will help walk you through all the different ways that you can solve the formulas, the differential equations that we will be using this semester.